In this video, we're going to be taking a look at the absolute, aka direct, aka just comparison tests. Lots of different texts will refer to this test as absolute or direct or just comparison test. So lots of different names for it. The idea behind this test is that we're going to compare the lesser known series to the known series, such as our harmonic series, P series, and geometric series. So thinking in our goal, how can we relate these series we don't know to the series that we do know? What the comparison test is exactly is, let's say that we have some point in our sequence. So for some n, such that for all the sequence terms after that point, if your one bigger series converges, then your smaller series converges. So I'm trying to state this in words. Our notation's a little bit different, but just once again, let's say there's some point, some integer that we call capital N, such that the sequences are it's always the case that 0 is less than or equal to an is less than or equal to bn. So bn has to be bigger past this point n. It doesn't always for all terms, but it has to be that for the tail end of the sequence, the bn is bigger. If you know that your bigger series converges, then the smaller series must also converge. So if you think about how our series can kind of relate to Riemann sums, it's almost like saying, well, I know that this function that has way more area under the curve has a convergent improper integral. So that means that this curve that has way less area must also be convergent, kind of like a way of getting a bound on our series. Okay, alternatively, let's say we happen to know that our an is always bigger than our bn past a certain integer n. These are all positive. If the smaller one diverges, then the bigger one must also diverge. So again, it's kind of like saying, well, I know that if this smaller series is infinite, then a series even bigger also has to be infinite. That one might be a little bit easier to get a handle on. Let's kind of try and sum these conditions up in words, because this notation can be a lot when you're first seeing it. So we'll call this one pushing down to convergence. And we'll call our second condition pushing up to divergence. Okay, aka for condition 1, if the bigger series converges, so must the small. And for divergence, if the smaller series diverges, so must the larger. Okay, and these sentences are not mathematically rigorous by any means, just trying to give you a little bit of a mnemonic to help you navigate this notation. Okay, so something to notice just before we move on and jump into some examples. So this only has to be true, this inequality only has to be true for all the numbers past some capital N. So even if your N was like 1,000, if it's the case that past the 1,000th term in the sequence, these inequalities hold true, you can use the comparison test. So it's all about the tail end of the sequence of the series, where it goes eventually. Okay, so now that we've kind of got, at least in general, what the comparison test is, let's look at some examples. So for each of the following series, we're going to use the comparison test to determine whether the series converges or diverges. So when you take a look at any series, we're going to gain over time, once we cover all of the different tests that we can use, we'll cover the strategy for how we can kind of figure out which one to use. But right, just kind of lining us up for that, when I see the series 1 over n cubed plus 3n plus 1, immediately the series that jumps to mind as being similar is 1 over n cubed. Okay, the series 1 over n cubed is similar because that 3n plus 1 in the denominator is really not going to have too much effect on this series. So let's try and see if we can maybe use this similar series to our advantage. So when I look at the two series, I want to have an inequality that compares them. So we're going to find the inequality relationship. Fortunately, the numerators are the same, and the denominator on our original series is bigger. So if the denominator is bigger, it's like comparing 1/4 to 1/3. Bigger denominator means smaller fraction. So I know that 1 over n cubed plus 3n plus 1 must be smaller than 1 over n cubed. Okay. Let's just take a look. Why? Because the denominator, excuse me, because the denominator is bigger. Okay, so if our denominator is bigger, we've got the one with the bigger denominator being smaller, and that inequality checks out. Okay, so now we need to make a note. Okay, are they all positive? Yes. Just kind of trivially, these terms are all going to be positive because our n's are the natural numbers starting at 1 going to infinity, so all positive fractions. So we have an inequality that sets us up to use the comparison test if we find it helpful. So now let's figure out what we know about the known series. Okay, this is the series we know. And what is known about this? In previous videos, we covered the integral test, and we used the integral test to show that a p series will be convergent when p, the power, is greater than 1. So it is known that this is a p series with p equals 3, which is convergent. Okay, so if I have something that's even bigger than my original series that converges, that means that my series must converge. By the comparison test, our series 1 over n cubed plus 3n plus 1, ranging from 1 to infinity, converges. Okay, so let's look at our argumentation. When we apply this, we find a similar series, we establish the inequality, we identify whether the known series converges or diverges, and based on what. So sometimes you might need to go through a little more work to show that your known series is convergent or divergent than what we did, but at least give some sort of argumentation like we did right here. And then we can come to our conclusion once we've established that our hypotheses for the test are satisfied. Okay, let's take a look at a slightly more difficult one. Okay, so we have 1 over 2 to the n plus 1. Our series ranges from 1 to infinity as per usual. And we're going to look at what is our known series. Okay, our known series, drop the plus 1. This looks extra to me. So I would say our known series is 1 over 2 to the n, which is better known as 1 over 2 quantity to the n. Because think about it, we can rewrite 1 as 1 to the n because 1 to any power is just going to be 1. So our known series is 1 over 2 to the n. Let's establish our inequality relationship. Again, because our numerators are the same, when we have a bigger denominator, we have a smaller fraction. And all of these will be positive because our n is positive greater than 1. Okay, and then we've got our inequality. What does our known series do? This is a geometric series with r equal to 1/2. So it is convergent. And again, in a previous video is where we explored geometric series to their full extent, and we concluded that when that ratio is magnitude less than 1, when the magnitude is less than 1, your series converges. So If we have the bigger series being convergent, by the comparison test, the smaller series must also be convergent. So by the comparison test, our series 1 over 2 to the n plus 1, n ranging from 1 to infinity, is convergent. Okay, let's take a look at another one. Okay, this one's a little more spicy. So our series that we're looking at is starting from 2, and that's a little bit different than usual. So we're starting from 2, and we're looking at the ratio 1 over ln to the n. So I would say the key here is for ln's, think about the fact that ln of n and n are eventually, they start off fairly similar, and then n kind of gives you a bound. So this one's not immediately obvious, but let's look at f of x equals ln of x. Looks like that. And then versus g of x equals 1 over x. Sorry, not 1 over x, just x. Okay, so notice how x gives you a bound on ln of x. It turns out that x is, as x goes to infinity, the line y equals x is actually bigger than ln of x. So we can make a comparison that 1 over ln of n. 1 over ln of n is actually going to have, ln of n is a smaller denominator, so the smaller denominator is going to be the bigger fraction. And all of these are greater than or equal to 0 because n is always positive greater than 2. Okay, and then what do we know about our known series? 1 over n. The series 1 over n is the harmonic series. Which is divergent. Okay, so by the comparison test, our bigger series must also diverge. Okay, so in these examples, we've kind of seen that we have some motivation for comparing series to known series, but in this last example especially, it demonstrates that sometimes the comparison that might be helpful might not always be super obvious. Practice will help you kind of get the hang of what to compare to, but also there might be another better way to compare, and not necessarily better for all instances, but just better in some cases. So this motivates us to study yet another comparison test, which we'll be studying in the next video. So in the next video, we're going to take a look at the limit comparison test, and it's just another way to handle comparing when you can't always come up with an easy comparison series. So I will see you then.